Um, Today's speaker is Nick Aybar. He is a grad student. He studied at UCSD in 2016, and he has done an exciting work on magnetic field distribution in Z-pinch plasmas. Initial work he carried out at Weizmann Institute, where he used the long current pulses. Now he's doing experiments on LTD pulsar at UCSD, where the current pulses are short. So that will be a good comparison uh, to see how the current distribution changes as a function of current, uh, price time, and pulse length. Uh, but today he will be focusing on some of the recent data he has collected on CESZAR generator. Nick, please go ahead.
Okay, thank you, Farhat, and thanks everyone for coming and listening. I hope you find it interesting. And feel free to ask questions while I'm going through. Yeah, that's not a problem to me at all. So yeah, as Farhat said, I'm going to be talking about magnetic field distributions of gas puff Z pinches on the CESZAR driver. And here's kind of the outline of what I'm going to be going over. So before I get into our experiments and results, I'm going to give some context and provide a little bit of background about Z pinches. I know we kind of have typically a diverse group, so everyone's probably heard of Z pinches, but I'll just kind of go over that in a little bit of that background and why we want to measure magnetic fields. And then I will talk about different ways of actually measuring magnetic fields in Z pinches and why spectroscopy is attractive and what it can kind of tell us. And then I'm going to go over the preliminary results, sorry, not the preliminary, but I guess the first set of experiments that we did at the Weizmann Institute looking at the effect of axial magnetic field and the instabilities on the magnetic field distribution. And then I'll get to our recent results on the CESZAR driver and how that kind of compares with the Weizmann data on our faster rising machine, and then to kind of talk about what the plans for the next set of experiments are. So yeah, first I'm going to kind of get into the background and give some context for these experiments. You know, maybe everyone's a little bit familiar with the Z-pinch, but you know, it's a system that's been studied for quite a long time. What it is it's a system that confines plasma using an axial current and its magnetic field. And there's a lot of different ways to do that. I have a couple of examples here. You know, you can do it actually with metallic wires if you're trying to produce X-rays of a certain energy range. And you know, this is just one picture of a wire array that was done on our machine here. You can also use gas puffs, which is something I've studied a bit more. And you know, those have different applications, and they have certain, you know, strengths and weaknesses. You can get a better known initial mass with the wires, and but at the same time, you can have better azimuthal uniformity with the gas puff, just as an example. So they have a variety of different applications. Probably most well known is for nuclear fusion. They were I believe the first attempt to study controlled nuclear fusion. Since then, you know, other techniques have been more focused on, but it's still studied for fusion today. One of the most well known is the MagLift program at Sandia, which actually uses kind of a laser preheat and then drives the compression with the Z-pinch current. They're also used to study astrophysical plasmas because you can reach these kind of parameter spaces, I suppose you could say, as similar to astrophysical conditions. And they're also a very bright X-ray source, you know, if you set it up right. And that can be used for a lot of different applications for radiography or absorption spectroscopy or things like that. So kind of focusing in a little bit more on the gas puff Z-pinches, and they can be you know, strong sources of X-rays and neutrons. And the way you can break that process down into 3 basic steps. first you need to form a plasma from an initially neutral, non-conductive material, and that's done with basically a breakdown event of the neutral gas, and that can be actually instigated by the current driver, or you can have a separate preionization system. So once that's done, current can start flowing through the plasma and set up a azimuthal magnetic field, and that field with the current is going to result in this Lorentz force, which drives the conductive material radially inward and accelerating it, especially in a fast gas puff Z-pinch. And once that material all runs onto the axis and collides with itself, it creates a high temperature, high density plasma, and this is where you get your high X-ray production if you're using that type of material. So this whole process, especially the implosion phase and stagnation, is heavily involved with the current and magnetic field are heavily involved there. So how they evolve and behave is really important to kind of understand and improve the Z-pinch for whatever application you're using it for. So one thing that's kind of also pervasive in Z-pinches, especially fast imploding Z-pinches, are instabilities. And this has been kind of known for a long time. It's kind of the main reason why it's not really, it hasn't been that successful for fusion. It's these instabilities. So you have a few different flavors of them. On the left, I have just an example of current-driven instabilities. And these show up when you basically have a perturbation in the interface between the plasma and vacuum. And you'll have so this example right here, you'll have if you have a small perturbation, you have higher magnetic field there due to Ampere's law. You can see that with Ampere's law, and that's going to increase the magnetic pressure there and actually further drive that perturbation. So then you get this kind of necking in the plasma. The same thing kind of happens in this other mode with a kind of bend perturbation in the Z-pinch can grow as well from the kind of a similar mechanism. But you also have in imploding plasmas, you have the magneto-Rayleigh-Taylor instability, and this is kind of the magnetized version of the common Rayleigh-Taylor instability, where a light fluid is pushing on a heavier, more dense fluid. And in this case, the light fluid is the vacuum magnetic field, which is kind of driving the implosion. And this is commonly seen in gas puff Z-pinches. So one way to mitigate that and deal with that is using an initial axial magnetic field. And these figures here are an example. This was published by our Fabio Conti in our group. And what we took some shots at the Nevada Reno facility, and basically scanned through higher levels of initial axial field. And you can see that with no axial field, you have these pervasive spikes that are kind of falling in even towards the stagnation time. And with increasing level of initial field, that is significantly reduced. So I thought it was important to talk about this problem, because this is why we're using initial axial magnetic fields to begin with, and why it's kind of important to understand what their effect is on the current distribution. So just kind of getting into more about why that's important to study. The kind of most basic pictures of, I guess, the most basic models of Z-pinches are not often well reproduced from ideal behavior. And one example is in this paper done actually by Weissman Institute, where they found that most of the actual pressure balance during stagnation phase is not, the magnetic field is not really responsible for it. It was found that the kind of dynamic pressure of incoming plasma was responsible for the stagnation pressure balance. So, and this kind of deviates from the more simplistic view of the Z-pinch process. So, the only way you can study that really is by looking at measuring the magnetic fields and measuring them experimentally to see what's really going on. So having more of that data is very important. And this is just a couple other examples of what has been studied fairly recently, and what the work that I'm going to talk about, the research that we've done, comments on, basically. So this is just a quick little snapshot of a study done that I think this was published in 2016. This was they basically varied the axial magnetic field and found that as they increase the initial axial magnetic field, the measured values of their measured and expected values of the magnetic field deviated heavily with the field and not without. And so we looked at that as well, and kind of found that our results were not really reproducive of this, and there's some reasons for that, and I'll talk about that. Another study that was kind of done recently was looking at the magnetic field distribution by actually measuring multiple points, and for a given shot. And we've done the same thing and found similar results, but in addition to that, we included an initial axial magnetic field where this study did not. So we can kind of look at that as well. So next I'm going to talk about a few of the different methods used to measure magnetic fields. And this little table here is kind of showing the most common techniques and how they work and what the drawbacks are. So the kind of most basic one is using inductive B-dot probes. And all these are is just a loop of wire that you put in the location where you want to measure magnetic field. And you can connect that to an oscilloscope and measure the time response of the voltage. And you can directly use that to measure the magnetic field actually at that location, in that loop, at least the flux, I should say. So these are simple to implement. They're pretty simple to build. I've made some myself for other reasons. But the problem with these is that they are inherently intrusive. If you're trying to measure in the plasma, you're going to end up perturbing it with this little probe in the way. And you're limited on spatial resolution. I mean, unless you put a lot of them, you're going to end up perturbing your plasma a lot more. So another common technique is Faraday rotation, and this is done just by sending a laser through, laser pulse through your sample, and the magnetic field will actually rotate the polarization of the probe laser, and you can measure that to infer what the magnetic field is. So this is a path integrated measurement. And you do need to get quantitative information. You need to know the density already that it's going through. And it can be limited, like it just doesn't work at all if you reach too high of density gradients, because the laser won't work in that case. Another more recent technique is the proton deflectometry. And the way this works is you send a pulse of proton particles, which are going to be deflected by the magnetic field, and you can actually get pretty good spatial resolution with this. Although temporal resolution with a small pulse. This is also path integrated as well, because you're sending a beam through. So the main drawback with this one is that you need a high energy proton source in the same lab as your Z-pinch lab, which is fairly uncommon. There's not a few places that have that. We certainly don't have that in our lab. So that's really not even an option. And there are some, it's a bit convoluted to get the quantitative information out of this as well. But so these are some of the drawbacks with that. Spectroscopy, on the other hand, is non-intrusive because you're just using emission. You don't have to send anything through the plasma that might perturb it. And you can get, in the right arrangements, you can actually measure locally the strength of the magnetic field, which is what we've done. So just to quickly talk about, I should say briefly, explain how the how the spectroscopy works. It's fairly simple. You have atomic levels are actually split by the presence of the magnetic field, which they're normally degenerate, and you produce one line in the presence of magnetic field, the levels are separated from each other, and this corresponds with a shift and split of the actual emission lines that you see. And this kind of figure on the right is showing a direct Zeeman splitting measurement, where this kind of black dotted line is where the line would be if there was no magnetic field. And you can clearly see that you're getting two lines actually that are split there. And the proportionality of that split is directly proportional to the strength of the magnetic field. And if in this case, this was a local measurement because the emission was from a very small source. So we knew wherever the emission was, this is where we're measuring magnetic field. So yeah, this can be used to provide a local measurement of magnetic field. However, the main drawback is this kind of direct approach of measuring splitting is basically never resolvable in the plasmas, the Z-pinch plasmas that we're talking about. And that's due to something called the Stark effect, where the kind of small scale electric fields that are due to the free charges of a plasma end up also perturbing the or shifting and perturbing the atomic energy levels. And what the end result of that is that you end up with a stark broadened line. You end up with the line actually being broadened over, so you don't see the splitting. But there are a few techniques that have been developed to get around that issue, including the ones that we're using. First the first one I'm going to talk about is this fine structure. I call it I wrote fine structure components technique. This was developed by Evgeny Sambolchik at the Weizmann Institute, and it hasn't been used very much in experiments. It actually has a pretty high uncertainty associated with it. But the way this works is it's not using any polarization or anything like that, which I'll talk about next. This actually just compares the line shape of two components of a multiplet, and that's what these figures are showing here. The red and blue are actually the two different components of a multiplet, and you can see that the kind of thinking is that the Stark broadening, the instrumental broadening, all the broadening mechanisms are the same between the two because they're in close spectral proximity, but the effect of the magnetic field on the line shape is predictably different. It's consistently different. There's a theoretical reason for that. It's comes down to the atomic energy levels. But this technique is very, I guess, exciting because you actually don't need to know the direction of the magnetic field. You can directly measure the magnitude, but there is a high experimental uncertainty that goes on with that as well. So another technique that's using spectroscopy, and this one is a polarization-based one, is I wrote here polarization perpendicular technique. This is what you can use if your spectroscopic line of sight is perpendicular to the magnetic field that you're trying to measure. And the way this works is by using polarization, you separate the sigma and pi components. And these also are predictably, they are split to different magnitudes from each other. So what you do in the experiment is actually use polarizing beam splitter to separate the two components. The pi components will be orthogonal to the sigma components, and that's why you're able to sort of do this. So if you're using this technique in a Z-pinch and you're looking on the side, on the basically down the Z-axis, or along the Z-axis, I should say, parallel to it, you can measure B theta because that's the parallel field. And if you're looking on the side, you can measure BZ, in fact. So to measure B theta with this has one kind of issue, and that's when you're looking parallel to the Z-axis, you have to integrate along Z. And this can create some problems because this is not really a local measurement in that case. And this paper was published quite a while ago, and they were not able to really get closer than 100 nanoseconds prior to stagnation. And that was basically because of axial gradients and along the line of sight, because it wasn't really axially uniform, their pinch. So the next technique, which works basically the same way, except in a parallel line of sight. In that line of sight, you're still separating the components with polarization, but this time the lines are going to be the light will be circularly polarized, and you're not separating pi and sigma, but you're separating the upper and lower of just the sigma components, so you don't see any pi lines. But anyway, they're circularly polarized, so you can pass those through a wave plate to make them linearly polarized, and then send it through your beam splitter and onto your spectrometer, and get a measurement of magnetic field by just comparing the spectral locations of each of those lines. So once again, if you're looking at the end-on view, like if you're looking down parallel to the z-axis, you can measure BZ using this technique, and looking side-on, you can measure B theta. And this is kind of the technique that I have focused on. This is what I've been using in both experiments. And just kind of one other point here is that, yeah, this is only valid when you're looking at the outer edge of the plasma parallel to the line of sight. And so from the literature, this is the only technique that I'm aware of that has provided local measurements of B theta actually during the stagnation time in experiments. So yeah, next I'm going to talk about the first set of experiments that we did at the Weizmann Institute that looked at the effect of the axial field and the instabilities that it mitigated on the distribution of B theta. So this is a kind of experimental setup of the Weizmann laboratory. They have a 16 microfarad capacitor bank with a 300 kiloamp peak current, and it's relatively slow for Z pinches. The rise time is a 1.5 microsecond, although our experiment was done on a shorter time scale than that. So we used actually, they have a kind of very nice set of diagnostics used at that lab with multiple spectrometers that are all time gated, and they can give you spatially resolved measurements. And we also had an imaging camera for each shot that produced a picture of the picture of the plasma for each shot. And this roughly, the densities here were initially about 5×10⁻16 per centimeter. And the temperatures that we kind of estimated were about between 5 and 15 EV during the implosion, just to kind of give a idea of what kind of conditions that we got here. Yes. Oh, and if I will mention pinch timing, and just to kind of explain what that is we also have a photodiode that's exposed to the light emission from the plasma. And when this reaches a peak, this is when we know that the stagnation has reached. And that's kind of what we use for the timing for a lot of the analysis. So this is just to give a bit of a closer look if it was a little confusing to see how the diagnostic work. So the spectrometers that I'm talking about is mainly the B theta temperature and a little bit the B theta spectrometer and a little bit of the temperature one as well. And so this is looking at a side-on view, so we can spatially resolve along, or I guess across that line of sight, so across the plasma column, but we are integrating along it. If you're looking at the central chord, it's not really true if you're looking at the outer edge though. And we pick one axial location at a time, although we were able to move this as well. The imaging camera is looking at just, again, side-on view. And this is kind of an example of how that looks for one shot, just to make it a little bit more clear. So the kind of first thing to look at of the results is the implosion dynamics. The imaging camera lets us do that. So even though we only get one shot, one picture per shot, one image per shot, we can plot those versus time relative to their each shot's stagnation time and put together an implosion trajectory. And so each of these images, this is one particular shot at a particular time. And the top here is without axial magnetic field, and the bottom here is with. You can see that we have, it's not crazy unstable without the axial field, but there are these MRT structures showing up, and not so much, at least qualitatively looking at this, there aren't really substantial instability structures forming. So, we compare this with 1D simulations done in track 2, just to kind of, I wouldn't say maybe better than ballpark, but estimate what the simple MHD picture looks like and how well our results match up. And they do pretty good. You can see we have a mainly matched implosion trajectory. However, the implosion is overestimated. The compression is overestimated without the axial field. And the reason for that is because the MRT spikes basically prevent that from imploding further. But one important distinction, I guess discrepancy I should point out, is the getting closer to stagnation time. There is a consistent delta, a consistent difference between the measurements and simulation. And that's going to be important when we talk about the magnetic field distributions, because it's a bit more pronounced when we look at, I guess the effect is more obvious when you look there. Yes. Okay. So I just also wanted to mention or kind of show the results from the temperature spectrometer. I call it a temperature spectrometer because we can use those emission to estimate the temperature. And I think this gives us an estimate of the temperature, which is good. But I think importantly, the data shows us the ionization distribution and the fact that we have a radial temperature gradient. So what this data kind of showed us was that we do have a radial, what's the way to say this? A radial ionization state distribution, where lower ionization states are existing in the interior part of the plasma, and even beyond where the imaging cameras look, and beyond where this kind of continuum emission is, there is some leftover, some residing plasma out in this area that's leading to this higher emission. And that's what this plot is kind of showing here, that we're still getting kind of bright emission from higher ionization states farther out, which is also important when we're looking at the magnetic field distribution, because that's going to affect things. So yeah, now I'm going to be getting into the results from the magnetic field. So this is kind of what the spectrometer is seeing. At one axial location, we have this fiber array that's looking across the entire plasma, and this is picked up by an imaging system with a lens and wave plates, and separating the two the two images that are, well, I guess it's one image that's separated to the two polarizations and sent to our spectrometer. Yeah, and so this is how that data looks. This is a picture of the raw data on the left. Right horizontal axis is the spectral axis, and these are the spatial axes. So it's a little bit confusing, but these are two actually mirror images of each other, and this is what you get from each of the fiber arrays. So as I said before, the data we can use is limited to the outer edge of the emission, and this was set up so that these are mirrored of each other, so they're both from these kind of ovals here. And so we plot these and fit a Voigt profile to them to basically determine the central location, I guess spectral location of each of the line shapes, and the difference between those can give us a measurement of B theta. So I kind of mentioned this in the beginning of what the previous studies were done by the Weissman Institute. So they varied the initial axial magnetic field and found that their expected and measured values were heavily dependent on that. So the horizontal axis on these plots are the outer plasma radius, and the y-axis is the magnetic field strength. And so the red dots are what they measured using spectroscopy, and the blue ones is a calculation of what they expect there based on the actual machine current using the B dot, and the same location is where the spectral measurements were made. So what this plot is showing here is that they found agreement between measured and expected values, and with increasing values of BZ, they deviated significantly. So that basically means that, you know, in this case, you must have some current that's flowing that's being shunted at a larger radius than they were able to measure with. And what they did also find in these studies was on the other spectrometer, they found emission from carbon ions, low density, farther out residing, like low density plasma, and they presume that this kind of hanging loose plasma, which is not moving inward, it's basically responsible for carrying the current. And yeah, so these are basically due to carbon contaminants that they didn't intend to be in the machine. So we kind of did similar experiment with a couple of changes at the Weizmann Institute. The idea was to try to reduce the contaminants. And so the results, what we found was that with or without axial magnetic field, we didn't find a big difference. And what we did was we basically had the Helmholtz coils, instead of being located within the vacuum chamber, we had a different set of coils outside of the chamber. The idea there is when you fire the chambers, when you fire the coils to produce the axial magnetic field, the coils themselves might actually liberate they might create some kind of dust or plasma that's making the vacuum chamber pour right when you're firing making the high vacuum not really so good right when you fire the machine. We also did several cleaning shots to try to clean off any of those contaminants that might be on the electrodes of the current driver itself. So all that work basically led to us having a fairly good agreement, although some of these data are lower than expected. And what we think is happening there is that they're just a little bit off of where, so this is, these blue dots are all measured from oxygen 3. And we know that there's some higher ionization states that are residing just beyond. And, we kind of saw that with the other spectrometer as well. But with oxygen 6, we often recovered almost every time of over 80% of Ampere's law. So, understanding your current, ionization distribution is a fairly good indicator of your current distribution as well. So there were a few instances where we simultaneously measured both ionization states, but lines from both ionization states. And given the spatial charge state distribution, we can actually, for one shot, get a radial profile of magnetic field with at least 2 points. And these results are basically shown here. And we have a pretty big difference with and without the axial magnetic field. So without the axial magnetic field, the results were not very consistent between shots. And we also found kind of a reversal of the initial, a reversal of the radial distribution, where instead of, so these solid lines are all produced by the track 2 simulations. This is what the 1D MHD simulation predicts. And without the axial magnetic field, in a couple cases, it at least follows that shape of it. And in a couple of other cases, it seems to be reversed. And we're not sure exactly why that is. If it's either because we're integrating over some MRT spikes that might mess up the measurement, so to speak, or if we're actually having some local inversion, some kind of bubble spike switching the location of the magnetic field and transporting that in there. But on the other hand, with the initial axial field, our results, while quantitatively are a bit shifted or a bit off, and there's a reason for that. The shapes of these distributions are consistent, and they basically follow what the MHD predicts. And as I said before, this discrepancy between measurement and simulation of the implosion trajectory is basically responsible for why these values appear shifted in time. It's because they're actually measuring at a point where the simulation thinks the plasma has moved a little bit further. So next and lastly, I'm going to talk about the experiments that we've done on the CESZAR LTD and see what kind of results we've gotten with a faster rising current driver. So again, this is the experimental setup that we've done that we have on CESZAR. The spectrometer arrangement is slightly different in terms of parameters, but the overall picture is the same. We have a imaging system with wave plates and beam splitter cube to produce the same kind of results. One thing that we were able to do on our machine, though, is not only fire hollow oxygen gas puffs, but like multi-gas, what's the way to say it? Like multi-gas puff setups. So we have what's called like a liner on target arrangement, where we have the outer gas shell and an inner jet. And the reason for that is, well, it's a bit more analogous to fusion type schemes, where you usually use a deuterium in the target region to use as your fusion fuel and basically implode another material onto that to compress it. Also, it lets us, when we switch these around, so that instead of having oxygen on helium, we can have helium imploding onto oxygen. We can see emission from the target region and measure the magnetic field there. And you also have a framing camera with 3 frames per shot, so we can get an implosion trajectory for each shot. And just before I move on, I wanted to mention again that this is a faster current driver. It's about a 500 kiloamp peak current in about 180 nanoseconds. And this is just an example of the current pulse. We're also using a photodiode. I think the most useful one for these experiments was filtered with a 3-micron aluminum filter. So these, just one example of the implosion trajectory we can get on CESZAR. These are, gated images about 20 nanoseconds apart from each other. And similar to the Weissman data, we can actually plot all of those images over time. And I did some kind of preliminary 0D snowplow calculations to see how well that matched up. And just to get sort of a ballpark, I'm still working on doing simulations in Hydra to better study this implosions. But yeah, I don't have more to show on that at the moment. So again, this is just kind of example of the raw data that we're getting. Roughly the same spectral region, same lines that we're looking at, and once again looking at the outer edge. And we did see for several shots both oxygen 6, which is this, which is producing this emission line right here, and a fainter, lower density and radially less extended oxygen 3 line. So that did provide us with a couple of radial distribution measurements that we made as well. So yeah, we do see both states. So first, kind of going over the hollow shell, the results from the hollow shell implosions. So what we basically found was that, and again, this is azimuthal field plotted against the radius. We didn't really reproduce well the what the results were found at the Weissman Institute, even without the axial magnetic field. we find that our measured data is falling consistently below the expected calculated data, which is calculated using, again, the B dot and the Ampere's law. And we're not sure exactly what's causing this. It may be that we're getting contaminants. We haven't specifically looked for them or observed them yet. And it could be other reasons for that, with the initial gas puff actually not being, our machine might not be very transparent to it. It might be getting bounced around, but we're still kind of working on that. So onto the liner on target data. So this data is showing the oxygen liner imploding onto the helium target. And we made measurements, of course, at the outer edge of the oxygen. And so this did provide a few measurements where, we did capture Ampere's law, but the vast majority of them were below that. And even these cases where it was kind of reaching what we expect, these shots are actually at the data collected from these are actually from the oxygen 6 emission, which is pretty far removed from the plasma. You can see this is out here at like 12 millimeters. And in these cases, the image, like the imaging camera, the MCP images are already showing a radius that is less than that. So we kind of confirm that, yeah, there's some oxygen, at least oxygen out there that's carrying a lot of the current, at least in some cases. So yeah, these are roughly similar behavior to the hollow shell implosions, although we didn't really capture in those data, we didn't really end up matching the expected values, but it's a similar trend. So next, looking at data that we collected from the target region. Again, this is kind of the same thing, and you might be thinking, well, it doesn't really make sense to compare with Ampere's law if you're looking at the target region, but actually we found that in a lot of cases, especially this data that was collected out here, the oxygen 6 was actually observed at a larger radius. So these are pretty large radii, even though the initial gas, the central gas jet is not, quote unquote, not supposed to be out this far. We're still seeing oxygen out there. And in these cases, this is kind of at the same interface as what appears to be on the imaging camera. Still, we were able to make measurements at a smaller radius, and we are working on MHD simulations to look at that. And I have a little bit of the preliminary simulations to kind of show here next. So, this is kind of similar simulations as were done, at least what I showed from the Wiseman data. So these were carried out in Hydra, and each of these curves corresponds to a different time, a different radial profile of B theta. And I put a little star here to mark the liner target interface. So everything left of these stars, at least in the simulation, is oxygen, and everything to the right of it is helium in this case. So this is to compare with those types of shots. So I just plotted here a few to make it clear, to make it easier to read the radial profiles of B theta in this liner on target configuration. So first of all, there are certainly discrepancies between the measurements and simulations. The timing is not well done. So I don't really want to focus on that. I more want to focus on the evolution, the difference of the evolution in radial profiles. So these are measured actually at fairly large radius, and as you move forward in time, from this pink one which is 90 nanoseconds before pinch, the green one is 60, and the red one is 40. The distribution is not at all becoming more like it doesn't show that the current sheath is moving inward radially. If anything, it shows that it's either not moving or it's potentially moving outward. And this is kind of consistent with this observation is consistent with the current profiles that we measured, as they don't exhibit an inductive dip, which is what you expect if your current sheath is actually moving towards the axis and creating a higher inductive impedance to the entire driver, which is not what we've seen. And I'll show that a little bit more later. So to improve the simulations, we definitely need better characterization of the initial gas density. These were done using, kind of rough estimates to provide some kind of comparison. And also, I mentioned I'm only showing a few, three plots here, three experimental points here, but we actually took some more. We have more than that, and it was a little bit messy, but yeah, we're getting the same results over, a good handful of shots. So we also, we can observe the same thing with the hollow shell implosions, which is what this data are. These experimentally measured B theta profiles show the same kind of trend over time, while of course the simulation is showing the opposite of what we observe in the experiment. Unfortunately, I don't have a good comparison of the dynamics of these particular shots. It's just sort of bad luck. So I can't say exactly where the outer plasma radius is from the imaging camera, but in any case, yeah, this is showing kind of the backwards trend. And also in these shots, we didn't get inductive dips either. So yeah, we think we can improve that if we have a better optimized initial gas density. And in fact, recent gas puff experiments on CESZAR have kind of shown that. So the left plot here is one of the it's one of the current profiles and photodiode signals from the oxygen data that I've just shown you. And you can see, healthy-ish looking current profile and a nice photodiode peak. However, there's no coincident current dip. And this is representative of basically all the shots that I've shown already. And this is another shot that was taken on CESZAR yesterday of a neon on deuterium for a different experiment, but this is a gas puff experiment done on CESZAR. And so with a better optimization, they were actually managed to see a high X-ray spike and a coincident current dip. Although not very pronounced, it's something, and it's something that I think will have an impact on the current distribution. So the next set of experiments I'm going to do are going to try to optimize that better and see how the current distribution looks while we have actually inductive notches in the current profile. So that's all I had to talk about. I will summarize what we kind of went over. So we did gas puff Z pinches on the CESZAR LTD and at the Weizmann Institute to study magnetic field distributions in gas puff Z pinches. We found by doing experiments designed to reduce contaminants resulted in good agreement between measured and expected values of B theta. So far, the experiments on CESZAR show that on that machine, the current has been flowing beyond the apparent outer plasma radius, even without BZ. And we're not exactly sure why that is happening, but it seems like we can kind of improve that, since recent experiments are kind of showing that they can be improved. Yet the data that we have found is compatible with the current profiles that we have, since we're not getting inductive dips. And in addition to that, the next set of experiments, we will also include the axial magnetic field system on CESZAR, which has already been built and tested, and to see what kind of effect that has on the magnetic field distributions as well. And also, working to improve the hydro simulations and run them in 2D to help interpret the experimental results. So that's the end of what I have. Thanks for listening, and yeah, happy to talk about this more if anyone has questions.
Thanks, Nick. Are there any questions for Nick?
Thank you. That's really nice work, and I especially appreciated the overview of Zeeman methods at the beginning.
Mm.
I'm curious, especially if you don't see the inductive dip, were you able to cross-time the radiation pulse that you did see to any of the simulations, Snowplow or Hydra?